Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Monday, August 29th, 2022. I'm delighted to be here with Professor Bradley Efron. Brad, it's great to be with you. Thank you so much for joining me today.
I'm glad to be here too.
Brad, to start, would you please tell me your title and institutional affiliation?
I am Professor of Statistics Emeritus at Stanford University. I guess I'm also emeritus from a department in the medical school, Biomedical Data Systems,
Brad, what year did you go emeritus?
last year.
Oh,
I,
brand new.
my hearing was giving out. That was the main thing.
Brad, tell me a little about your affiliation with medical issues at Stanford.
Okay. So I got here in 1960. I was a student, then I was an assistant professor. While I was a student, I started uh, participating in the medical school consulting. My advisor, Rupert Miller, and senior fellow Lincoln Moses uh, ran a weekly consulting workshop in the medical school. The medical school had just moved down from San Francisco into into Palo Alto, into the Stanford campus, and it was a wonderful experience working with them. It was much livelier in a certain data sense than the pure statistics I was getting over in the stat department. And so I was a half-time member of the medical school faculty for all those years, 55 years, whatever it was, more than that actually. And the during that time, I'm not a doctor and I'm not any good at medicine or anything like that. What I do is, and have done, and I'm still doing now, is consult with people in medical school. People run experiments, and they get a lot of data, and they're not trained to get the information out of the data. They're also not trained very well a lot of times to ask exactly the right questions and stuff. So work with medical researchers who are by and large smart, honest, hardworking people. It's hard work. Human medicine is a much more complicated subject than say quantum theory or something like that. It doesn't work that way. It just doesn't follow the rules the way it should. And there's so if complicated is a measure of how hard something is, medical research is about as hard as it comes.
Uh-huh.
And so I've always been there working with it. I worked early on things like various kinds of leukemias and stuff like that, and worked with very good researchers. And what was different in 50 years ago was the experiments tended to be smaller and the data less. It was harder work getting things done, but people were clever about it. So one of the questions was early questions: does it help cure leukemia, non-Hodgkin's kind of stuff, to add radioactivity? That is, you're going to put people at the end of a small linear accelerator, which was sort of sounded crazy at that time. Well, no, that's the way they do it these days. And so I learned a lot, and it's always had a big effect on my research, and my general attitude towards statistics was always had something like applications in mind.
Brad, before we turn to your own research, you've been at Stanford so long. I wonder if you can talk a little bit about the development of statistics at the institutional level at Stanford over the decades.
Sure. Stanford, in the last time they did a review, Stanford statistics department was far and away the most successful department. It Everybody agreed it was the best department. Everybody in the country agreed it was the best department, and that wasn't an accident. The university, for some reason, has always been quite supportive of statistics, and it got going at Stanford after World War II, and maybe 10 years after that, it got really going. There were a couple of people. Herb Solomon was very well connected with the Naval Research Institute. It was during the time when the armed forces could still directly support research, and they got quite a bit of money, and the university was forward looking in having a statistics department. That wasn't so obvious, and it really got going. By the time I got there, it had a lot of momentum. It was probably the second best department in the country when I got there. The first best being Berkeley, where the famous Dr. Neyman, Professor Neyman, collected wonderful researchers and sort of send some of them to Stanford. The trouble they had with the loyalty oath, which was a long time ago, sent Charles Stein to Stanford. Charles was the greatest mathematical statistics guy, and so when I got here, there were famous people here, and famous meaning that they really were good. It wasn't that their name was in the paper. The Chernoff and Stein and Manny Parzan, Rupert Miller, who I mentioned already, and the department was a very exciting place to be. It was as a subsequent, you can see from point of view of a long time ago, it was the end of a successful end of a long arc of mathematizing the field, and that was very good. It was really done at a high level, but it had its downside, and the downside was that it wasn't as useful. The mathematized statistics isn't what the world was calling for in terms of analyzing data. It was what was needed to put the field on a solid basis. But subsequently, for a long period of time now, there has been a movement to make the field more useful to people like the medical school, but also everybody else too. And that's been accelerated by computers and things like that. So the field came up strongly, and the department didn't rest on its laurels. It's got new good people who work in those areas.
Brad, in what ways has statistics become more interdisciplinary throughout the years at Stanford? In other words, opportunities to collaborate with other departments or even schools in Stanford.
Okay, so that's a nice question. The statistics by its nature is interdisciplinary, though that's not exactly the right word. It's sort of superdisciplinary in that there is no, astronomers have stars and geologists have rocks and chemists have chemicals and stuff. There is no natural statistics. The statistics, the raw material for statistics is what other scientists do. And so it's naturally interdisciplinary. During all this time, more than half the members of the statistics department have joint appointments with other departments: math, computer science, electrical engineering, the medical school, things like that. So it is naturally mixes with other disciplines.
Brad, I want to turn now to your own areas of expertise. So perhaps at the broadest level, if someone asks, what kind of a statistician you are. What's the most digestible answer, one that the man on the street can understand?
Okay. Uh, well, I can tell you what kind I'm not. I'm not the kind who does high math kinds of theory. Uh, I've been somewhat in the middle. But if you made a social diagram right now, my own work, I try, I've tried to make it as useful as possible, but that doesn't mean going around and working specifically with people, say in the medical school or astronomy people I've worked with, and stuff like that. I mean, in a general sense of doing stuff that people could use. So I worked a lot on confidence intervals and things like that, families of models that people might use. And so I'm not as applied, say, my colleagues, Rob Tibshirani and Trevor Hasty and Jerry Friedman, they've worked much more with making statistics to take advantage of the computer age. They have books that have had a very great effect. I think Rob is the most quoted mathematical scientist right now. He's got something like 300,000 citations or something. And I rely on them to help me be more with it when it comes to doing stuff that people would want in the computer age. But what they want in the computer age isn't necessarily just computing. They also want. I still get small data sets, and I still have to work on them. And still, so I have one right now with 480 people who each they were patients in some medical thing, and they each have 9 kinds of symptoms, and what's the relationship between the symptoms and the people, that kind of thing. That's not an enormous data set, but it's hard to weasel out the right idea. And so I try and work on stuff that's at least sort of useful. I'm just publishing a book. It's at CUP, right, the Cambridge, on exponential families, which is parametric families of distributions. Parametric meaning some kind of model like you learned at Caltech with exponentials and stuff like that. And but before that, I did a book on with Trevor Hasty on called Computer Age Statistical Inference, which reviewed what had happened to the field since computers came in to the field around 1950. And so I'm sort of a general worker. I'm not as I'm not as mathematical as the more mathematical guys in the department, and I'm not as applied as the more applied guys in the department. I'm somewhere in the middle.
Brad, what about another binary in the spectrum on which you lie? The difference in statistics between an experimentalist and a theoretician. How does that work in your discipline?
Well, I like to say that physicists have a third category called phenomenologists.
Yes.
I'd say I like it. And phenomenologists are people who are supposed to take the theory from the theory guys and bring it over to the other guys, and they're connecting links. And I like to say I'm a phenomenologist. I think that makes me feel good to have a nice long name like that.
Brad, in such a long and varied research career, what are some of the themes or research questions that have always remained close to what's important to you?
Well, there's the questions of accuracy. There's 2 main kinds of statistical questions, maybe 3 nowadays. I wrote a paper called Prediction, Estimation, and Attribution. And those 3 are things. Prediction is obvious what it means by prediction. These days, that's big in the news. You read about, you know, and I've worked with some of those things, but I'm not. I have to go to my colleagues to talk intelligently about stuff like that. Estimation is you get some data and you're interested in some number, but you don't see that number, and you have to estimate it somehow. And that's when you get to things like how accurate is an estimate, and how do you get a confidence interval for that estimate. And then attribution is you have a bunch of possible causes. In that example I was saying, there were 9 different things that were important maybe, and you wonder which of them are actually important. And I've been working more in the accuracy field. So my most notable thing, or the thing that got me the most credit, is the bootstrap, which is a method of assigning accuracy to an estimate. So you go out and you get a whole bunch of data, and you have a parameter you're interested in, like say the mean of some quantity, and you can estimate it from the data, but how accurately are you estimating it? And that's what I've worked on a lot. And the exponential families that I talked about are a meta method for, it goes back ways for getting at that problem. And I've tried to get the theory of that to work what I call automatically. That is, there's some statistical methods are much easier to use than others. If you want to estimate something, one way is to try and find the best estimate, the one with the smallest variability that's unbiased, best unbiased estimate. Another way is to use maximum likelihood. Try and choose the parameter, the thing you're interested in, the value of it that maximizes the likelihood of what you've seen. The first of those, unbiased estimation, is hard. You have to think of a new idea each time. Maximum likelihood is automatic. You can write one program that does it for every game. And I've been trying to make a theory of confidence intervals that is automatic. And it's become possible because of massive computing. It's unbelievable how fast the computers are now. I mean, literally 10 million times faster than when I started, or maybe more than that. And they're more than just fast, they're so convenient. The engineers have done such a wonderful job of making them. This little thing I'm talking to you on now is so amazing. When I was a kid anyway, there were all predictions about what the world of the future would look like, and there were autogyros in the sky and stuff. Nobody ever predicted this kind of stuff, and it's just incredible.
Brad, have you ever pursued a career as a public intellectual? In other words, communicating the technical aspects of statistics to popular audiences so they can appreciate the role of statistics in sports, literature, politics, healthcare, you name it?
Oh boy, you're just my guy. In my dotage here, now that I retired, one of my projects is to write such a book. And I'm writing such a book called To Think Like a Statistician. And it's about how statisticians think. And it's just about that stuff. And boy, it's hard to do.
Yeah.
I'm not a natural friend of the public or something like that. I have people, my friend Percy Diaconis, who's a good mathematician and statistician, is a natural at that kind of thing. I'm not. And I sure wish I could write better. I'll tell you that.
But you're pushing yourself in retirement. That's great.
Yeah.
Brad, what have been some of the big debates in statistics, and where have you come out in some of those debates in your career?
Okay. There's a classical debate that's been going on for almost 200 years, which is between the Bayesians and the Frequentists. And it's basically a debate of whether in approaching a new problem, like I told you, the one I told you about, is whether you get to use past information or not. And it sounds like, well, you should always use past information. But if you do, the question always comes up, which past information? And if you want to have, another, people want to use as much information as possible, but they also want to not have their methods adulterated by opinion. And so the question of whether you can use opinion or not is important. And that, the Bayesian theory, which goes back to 1763, is a way, and a very important way, of using past information to update. The idea is you start with some opinion, you get the data, and the Bayes theorem is a machine for updating your information. You had odds, it was 10 to 1 in favor of something. Before you started, you got some contrary information. Maybe now it's only 3 to 1. How do you do that? And that's a wonderful theory. But in the 20th century, one person, R.A. Fisher in England, showed that it was possible to have a non-Bayesian theory that was effective and in some sense optimal. And that's the frequentism works basically within the framework of any data you have, not bringing in what was past. The question that I've always been very interested in is what's the boundary between those two, and how can you get the advantage of both of them, and how can you bring how can you make a Fisherian kind of answer mesh with there's sometimes very reasonable Bayesian answers. How do you put them together? So that's the biggest back and forth over the many years has been between Bayesians and frequentists. Frequentists are, for the last 100 years, been dominant, but not exclusively so. And Bayesians, there's a lot of good reasons to do Bayesian research, especially in some areas where there is a lot of useful past information. If you're running a drug company and you keep running tests on lots of similar drugs, each data set doesn't have to stand by itself. That seems obvious, but it's also obvious is the Federal Drug Administration doesn't want you bringing your opinions in to your data analysis. They don't believe them, or maybe they can't afford to. So there's a lot of tension there. So that's been the main back and forth. There's been another controversy. I almost say controversy. It's not like we read in the papers about whether is Trump going to jail or something.
An academic controversy.
Between what do these prediction algorithms do, like deep learning and stuff like that? What are they doing, and is it enough? Or they tend to be. There was an article in the paper today of New York Times about a guy who works on that, who says it's not enough. You don't understand anything. They're good at making point predictions or something, but you can't understand what the predictions are. So another controversy is what are the roles of these machine learning is the general term methods compared to classical statistics. How do they fit in? And there's some controversy there about, are they doing what you want to do? Have they made classical statistics irrelevant or something like that? There's a lot of room for controversy or at least uncertainty in statistical arguments, because, as I said, there's no natural statistics in the universe. You can't compare your answer to something that's rock solid from a measurement that you make, and that makes the field difficult to progress. Has to be after a while you can see if something's working or not working. So one controversy has been about whether Bayesian answers tend to be biased. That is, they're biased in the sense that they aren't if you get if I have 50 numbers that I've gotten by repeating, looking at something, and I want their mean, taking their average is unbiased. If I have Bayesian answers, Bayesian information, it's not going to be unbiased in that sense. And uh, there's some question. One question is how much bias will people who work in the field stand? You can if you can say in the long run this is a great thing to do, but for your particular question, I'm estimating something with quite a bit of downward bias. Then people get nervous, and so that's been a kind of question: is what is it that we're doing? And needless to say, people work hard on trying to get the answers there.
Brad, as you alluded, there's been fantastical growth in computer power over the course of your career. In what way has that made your work more efficient, just as a tool? And in what way has it made your work different, simply that you can do things that otherwise would not be possible?
Well, the when I started, uh, there was almost no electronic computation, and I had a desk calculator. And I don't know if you've ever seen one, even that they're large, bulky, noisy things that take 15 seconds to multiply two numbers and stuff like that. And you were grateful to have them. And when I actually started working much over the medical school, for example, I had I had Jerry Halpern, a guy who worked here, who was good at the computer, and I'd give him some analysis to do, and he'd bring it back the next day, and then we'd proceed like that, because I couldn't do it, and now I can do everything myself, up to a point, and I can go so much faster. I must be 100 times faster than I was before, and also I can do much more ambitious analyses. The wonderful way the computer programs are available to do exotic things, but packaged in a way that I don't have to know what all the nuts and bolts of it. If I know what the idea is, I can use it. So I go much faster now, and I'm much better. Uh, I don't have to rely on somebody else. I actually understand what's going on well, and I can take it apart and do graphs. It was incredibly hard to do graphs and figures before. If you've ever tried to draw a curve with doing the X's and Y's, it's not a natural thing. So I'm a grade B computer user, but that's a lot better than I used to be.
Brad, beyond academia, where have we seen the influence of your work out in the quote unquote real world, whether it's industry or government? What are some of the ideas that you've had that have had an afterlife beyond your work on them?
Well, I don't have 300,000 citations. I have a lot, but most of it's I mainly worked inside statistics. I think if I was going to say what I do, I'd say it's connecting up ideas in statistics and extending them somewhat. But the bootstrap had a lot of influence in the sense that people use it a lot. And if I run into people in other fields, they'll say, "Oh, you're the bootstrap guy," or something like that. Uh, there, my colleagues that I mentioned, the Hasty and Tipshirani and those guys, they've had a big influence on how the machine learners do their work and stuff like that, and that's a really good thing. Um, it's easy to overstate one's own influence on things, and uh, I, I like what I've done, but I don't. The man in the street is not going to benefit all that much unless he lives in a very good street.
Well, Brad, let's go back in history now to establish some context before you got to Caltech for your undergraduate. Growing up, were you always mathematically inclined? Did you sort of naturally gravitate in that area?
So my dad, Miles, I named my son Miles, incidentally. My dad, Miles, was a smart guy who didn't get to go to college much. He started back in the time, and he was actually a smart man, and he was a salesman and things like that. And he loved math things, and he loved keeping score of baseball games. He taught me. We'd sit around doing baseball scoring. I don't know if you've ever drawn one. You draw little X's and things of
Hmm.
people going around and stuff. And so I liked numbers when I was young, and I guess I thought I was a mathematician, sort of. Uh, my the My high school had wasn't St. Paul Central, big high school with multiracial, as we'd say these days, and pretty good, some pretty good teachers in I liked my geometry class and I liked my trig class. It was really good. No calculus at that point. Um, and so I think I was set up. I think I thought I wanted to be a mathematician. Uh, I'd go to the St. Paul Public Library and check out math books and not understand them, but sort of hold them. And uh, that was pretty much how I got to my I had an uncle who had moved to California, and he gave me a a subscription to Time magazine, and they at one point on the cover of Time magazine was Lee DeBridge, the president of Caltech, and I followed the one student, John Anlin, through his $80 a week uh, trying to keep up with all the people at Caltech and stuff. I said, that's for me, when you're 17, these things seem like a pretty good idea.
I was
And
going to ask you what your point of connection at Caltech was. It's so far away, how you even knew about it.
ah, and I got a really lucky break. The year that I was graduating high school, they started the Merit Scholarship Program,
Hmm.
and I won. And at that point, it was a full 4 year ride, and I applied to Caltech, and I'm sure they wouldn't have let me in if except for the scholarship. And the guy came out. I forget his name. It was at a time when they sent a faculty member around to interview every prospective student, and he came. He told me that I'd probably be a B- student because they never had a student from St. Paul Central, and uh, this just encouraged me. Oh man, I can do it. I guess I used to be confident, uh, and that's how I got to Caltech. There was no other place I really wanted to go.
Brad,
I
what year did
thought I
you
was going to.
arrive? What year did you arrive? Was it 1956?
Yes.
What were your impressions when you first got to Pasadena?
Well, I took the train to Seattle because I have a brother. My older brother Arthur was in Seattle, and I took the train down, and I was stunned. I'd never seen the ocean. I'd never seen a mountain. Uh, I woke up at 4 in the morning, and there was Mount Shasta going by. Then we got to uh, Oakland actually, and there was they at that point the train would be put on. You had to get across the bay. It involved a ferry boat, and I looked, and there was San Francisco across. I hardly even knew about San Francisco. It was an incredible city, and I thought, gee, if this is San Francisco, what's Los Angeles like? And we went down to Los Angeles. I was picked up at the uh, Union Station by an upperclassman. They'd send them. His name was Brett, and I wish I could remember his last name. And I was driven. I'd never had seen a freeway before. Got to Caltech. It's pretty small. I like that. And I was horribly uh, homesick for a few weeks, but then acclimated. And in those days, at the beginning of Caltech, they didn't tell you at Stanford. These days they tell the students how wonderful they are and how great they are. That wasn't the attitude. In those days, it was look to the left, look to the right. One of those students is going to be gone if you don't really work hard. And somehow that didn't scare me. I don't know why. I started meeting smart people. You know, everybody was real smart. That was the first year, I think, that all the students that were admitted had 800s on both their math and verbal SAT scores. So everybody was a top student, and they really were smart people, and the faculty was smart, but the students to me seemed smarter to me. It's just because I was closer to them, probably, and stuff like that. But I joined Ricketts House, and I really liked having a bunch of friends around, and the people were so clever. And
Did you get involved in any of the pranks?
sort of as a sideline, I'd see them doing the pranks. I remember, I remember Jim Sorensen was one of my classmates who was a prank instigator and stuff like that. And they, they'd at one point, there were four dorms in those cases. I can't remember them. Ricketts, Black. Wow. Sort of forgot the other two. Each one had a stand-up piano in the lounge, and at one point the pianos started disappearing one by one. Eventually, they were all found in one student's room. I didn't see how he could sleep in the room, but somehow he managed. He was doing it as a prank, of course. And I thought that was about right.
Brad, was the plan from the beginning for you to pursue a degree in mathematics?
I thought I was going to be a mathematician, and it took me a few years to realize that even though I could get good grades, I wasn't a natural mathematician. I just didn't have the feeling for abstraction that matter mathematics has. I think.
And you mean pure mathematics?
Yeah, that was the kind they taught. And my co-student Al Hales, wonderful mathematician, has had a wonderful career. And when I look at Al, I'd say, no, I can't do that. Somehow Galois fields just seem like the natural thing to Al and stuff like that. And I began to get worried about my junior year, that this doesn't seem to me like what I'm good at. And one of my professors, Ward, I can't remember Ward's last name. He let me take a reading course in statistics. There was no really statistics courses. I got the book Cremier, Harold Cremer's book, which is very old-fashioned by today's standard, but it was a good book. Cremer was one of the leading guys. It was written while Cremer was under house arrest, essentially, in Sweden during the World War II. And I read that book, and it made me want to be a statistician. I wasn't even clear there was such a field when I started on that.
Brad, tell me why. Why did this book speak to you in the way it did?
The mathematics, by and large, seem more realistic to me. There's sort of two main ways that people convey mathematics. And one is the theorem proof kind of approach, which is the way most textbooks present mathematics. If you were going to take a course in complex variables, that's how the book would go. But the trouble with the theorem proof point of view, a theorem is a worst case kind of entity. It says no matter how bad things are, what I say is still going to be true. No matter how bad you try and make them, given to the limitation, given to the restrictions I put in the theorem. And worst case isn't great for applications. And so there's another way to teach mathematics or think about mathematics, and that's things like calculus and linear algebra are taught differently. You're sort of in the center of the field. You sort of look at the things that work most of the time, like linear linear fit or something like that, or that kind of thing. And the mathematics of the Cromera was more like that, and appealed to my mind as a kind of thing I could do. And I still have the book. It's sitting on the shelf behind me, as a matter of fact.
Brad, who were some of the professors at Caltech that you became close with or who were really formative in your intellectual development?
Well, I hate to tell you this, but I was sort of a loner, and I didn't get terribly close to most of them. I had people there who were very nice to me and stuff like that, and but I didn't have intellectual heroes in the math department. If I had heroes, it would be guys like Pauling. Linus Pauling, who taught the chemistry course, of course, or George Beadle. I'm sort of an introspective person when it comes to science, and I don't think I reached out much. I don't think I took full advantage of what Caltech could have given me. Some of it was Caltech's fault. It's a small school, and they didn't have a statistics faculty, and they didn't really even have a computer science faculty at that point. It's just starting. Maybe that was good. I might have been fallen into computer science otherwise. And but I liked some of my courses, but I didn't love them. And not long ago, I was going through some old stuff with my wife, the old box of things, and I found my transcript full of A's and A pluses of courses I couldn't remember even the name. And, but I did learn something very valuable at Caltech, and that was the value of cleverness. And they really taught that in the courses. The average test was an IQ test, and it wasn't a memorization test.
Brad, what do you mean by cleverness? What does that mean to you?
It means that if you're given a problem and it isn't a question of just slogging your way through it, you have to think of a way of finessing the difficulty of the problem by some insight that makes it easier. And so there were you took physics, the standard physics course at that time. Professor Strong taught it, and there were strong problems. There were 100 problems that had levers and pulleys and people, trains racing towards each other and stuff like that. And when do they meet and things like that? And each one had a trick in it. And the idea that you don't make much progress by facing new problems head on by just slogging through, but you try and see what the weakness in the problem is and exploit it. That's a thing that's very Caltech, and I've always felt I benefited immensely from being around people, raise the game, that kind of thing. It definitely made me better at that sort of thing. I've been editors of the main magazines and journals and stuff like that. An awful lot of the papers do slog through, and there's hardly ever a time you can just overwhelm something interesting. But there's a few people and a few papers that somehow manage to cleverly exploit situation, and lo and behold, something happens. The ideas are the coin of the realm in science, and maybe I'm just saying it pays to have an idea. And an awful lot of papers are written with no real idea in mind.
Brad, how did you come across the idea that statistics was a discipline that could be pursued in graduate school?
There was, well, that's a funny thing that happened. When I went up, I'm trying to remember, I had my Cremier book, and that was obviously a statistics book. He said it was a statistics book. So I thought that was sort of for me. And I went up, it was time to apply to graduate schools, and I applied to Berkeley and to Stanford. And I went up and made visits, and they both welcomed me with, I needed, of course, a fellowship. But Berkeley sent me a postcard saying I was in, and Stanford sent me a really nice letter. So I went to Stanford, and that determined half of my life. And incidentally, the two departments are still very close to each other. When I got to Stanford, I found that my recommendations from Caltech had said something like, "This guy is too smart to be a statistician. Put him in math." And so I was admitted to the math department. It took me another year to actually get into the statistics department. And I thought, oh well, I'm a real good mathematician, and statistics should be easy, but it wasn't. It was hard, and it's got a certain kind of feeling to it. The ideas, there's just too much. You can't mathematize the field. You have to have some feeling for where you're going, and that's what being trained as a statistician is about, is learning what's the effective ways to think about data analysis and how you might make tools that were good for data analysis.
Brad, was it always clear to you that you'd pursue graduate school, that you would not enter industry after undergraduate?
I guess so. I didn't. It was a time when a lot of the people who graduated from Caltech went to work in the defense industries.
Right.
And there was money to be made, but somehow I never thought of it that way. When I look back, I'm surprised how young I was and how little I knew about the academic world or what a life would be like. And of course, I think I made the right choice, but maybe I'd be rich, billionaire now talking to you. Oh, you wouldn't talk to me then. Yes, somehow it seemed natural to go to graduate school. And maybe that was Caltech talking, because of the way, Caltech really did have a wonderful intellectual atmosphere. By intellectual, I just mean smart. The people at Caltech are really smart, and at least that was my opinion when I was there, all up and down the line. Lee Dubridge was a very smart guy. He was a wonderful administrator. The various professors were obviously smart, and the teaching assistants were real smart, and the students were smarter still, I thought. And it was. I guess I felt that I wouldn't be good at earning a living in the regular world. Maybe the academic world was right for me.
Brad, when you got your bearings in graduate school at Stanford, what aspects of your undergraduate training were really useful, and what were the areas where you had to learn as a brand new discipline?
Well, I had never taken a statistics course, whereas a lot of my fellow students had. So I had to get that. But like I say, uh, I had enough good mathematical training, so that wasn't going to scare me. But uh, I didn't have any real scientific background, and I didn't have a lot of good feeling for that. So that was difficult for me at first. Why you learn things? You could take a statistics course and you learn something like a standard error. Why did people choose that definition? What's so great about that and things like that. Uh, the um, I and once again, I think what stood me in good stead was thinking more cleverly about the things, and that was definitely Caltech job stuff. And the uh, I did feel at home in an academic environment, and I think I should give Caltech some credit for that too. I My own home, my actual home in Minnesota, sort of disintegrated. My dad got sick and died, that kind of thing. My mom was dead, and so but Caltech was my home to the way I felt about it. And
Brad, in the way that as an undergraduate you never felt quite at home in mathematics, what is your distinct memory of feeling that statistics really was right for you, that intellectually you did feel home in that discipline?
I think it came more in over at the medical school where I was working on data analysis problems with Rupert Miller and Lincoln Moses and stuff like that. But when I'd feel like I really was being effective in analyzing data and that my theoretical stuff, but it's still sort of amazing to me that statistics actually does work. You think of these theories that seem maybe like they're rather arbitrary. No, you go out in the field and try and do them, and most of the time something comes through. You actually do help doctors understand their data and stuff like that. So I started feeling more of a mastery of the combination of what I was studying and how it might be used.
Tell me about developing your thesis project. How did that process develop?
Uh, it was once again, it's me being sort of a contrarian. I just started putting together stuff on probability of geometric objects and things like that. And there's an ancient topic that goes back to the beginning of the 1900s called geometric probability. I got interested in that. And in geometric probability, the random objects rather than points or numbers are things like circles and lines and stuff like that. And I was very at home with that. I have a good geometric feeling for it. Maybe I should list that as the third way to do math.
Mm-hmm.
And uh, I started putting together things like that. And I worked one summer at SRI working on the perceptron, which was an early version of deep learning and stuff like that. And I proved the theorem about it. And so I finally, they wanted to get me my degree and get out of there. So I put together some 4 or 5 of these kinds of things it's called Problems and Probability of a Geometric Nature. And there's something like 4 or 5 different topics, and some of them were published and some of them weren't. It's nothing like I've ever done since then. But it did give me the feeling that I could do research and that I could think of something that was new, not just finish somebody else's idea.
What was the process of determining who your thesis advisor would be?
Uh, uh, Every time I say that, I'm beginning to realize that I've taken a rather strange path to this day right here, sitting here. Uh, my when I got to uh, finally got in the stat department, I found that the person that who'd been at Caltech, whose name I'd heard, Sam Carlin, a major figure uh, of the mathematical kind, was having a big fight with the rest of the stat department and was leaving to go to pure math. And I started as a student, and I actually wrote a good kind of problem success thing for him. But he said that he wouldn't keep on with me unless I switched back to mathematics, and I wasn't going to do that. So my uh, Rupert Miller was a young assistant professor at that point. A wonderful man, died early. Uh, Clear thinker, very clear thinker. Could if I went to a talk and Rupert was there, if I missed the talk, or even if I didn't miss the talk, I'd look at his notes. They'd be very simple, just the line here, a line there, but it just would say what the guy had done. It was clear thinking is a wonderful thing. I wish I had more of it. Uh, and so I got to be Rupert's student, and partly it was because of the connection with the medical school and working over there. And uh, and then Herb Solomon, the guy who got all the money from Naval Research Institute, was a wonderful man also, and he helped support me and talk to me about things like geometric probability. So I drifted over to Rupert, and he let me put together the thesis out of several things, including one part of it was with my roommate at that time, Tom Cover, who had come from MIT. I met him when I first came to Stanford. And uh, Tom, a wonderful guy, he also died about 10 years ago, 12 years ago. And he and I were roommates. We wrote part of his thesis, and my thesis was a joint topic. One of the reasons I felt more comfortable when I got to Stanford after a while was I met some people in my dorm that turned out to be lifelong friends, Tom being one of them. Lou Padula was another guy. And the dorm was a horrible place, but the friends were very good friends, and that made me happy. So anyway, I sort of got Rupert to be my advisor, and he was always helpful. And I worked with him later after I got my so okay. So now I've got my degree, and where am I going to go teach? So a position opened up at Stanford, and I applied. And the Stanford has the department has had a long-standing rule against hiring your own. I was listed as the third choice, and the first two turned it down. The first one was my Caltech colleague, Larry Brown, who was a very good statistician. The second one was a guy from John Bather from England, also excellent. But thank God they both turned it down. I didn't have to go back to the University of Minnesota, which was my next choice. And there I was at Stanford still.
Brad, what were the central conclusions of your thesis? What did you see as your contributions to the field at that point?
I had no coherent view of it. I was still more of a mathematician than a statistician, and I was still not really at my full natural strength that eventually I showed long after that. However, I've always loved geometric probability since then. Nobody else does. It's a field that's almost non-existent. But every once in a while, I'll take out my old book and stuff and look longingly at it. So here's the kind of question you have. You have a plane, and you have normal distribution in the plane, uh, X, Y, and you draw several hundred points from that, and you try and draw the smallest um, polygon that will contain all the points. What's its area? What's its expected area? So that was the kind of thing I worked on. And no, it wasn't very useful. And no, I don't think about it much anymore, but I really like doing it. And Tom and I had fun working together on things. Tom went on to become the leading information theory guy in the world, and much missed. He was, but everybody agreed, a fun guy. Fun guys are not so common in the statistics world. He was an engineer, but he was really a fun guy.
Brad, from being the third choice to join the faculty, what did you feel were your prospects of tenure as an assistant professor?
Uh, I never worried about it. I started after the thesis, I started getting my feet on the ground about statistics. I started writing pretty good stuff, and I just assumed I was going to get tenure. Yeah, I always worry about things, but I never worry about the right things. I seem to not worry about getting tenure when I should have worried about it. Uh, and As a matter of fact, it got pretty quick. Um, and uh, the Somehow it seemed like my right. I don't know why I thought that, but I started doing good work, and I did have ideas, and uh, the my friend Carl Morris, he'd been my Caltech friend, then he'd come back and been my Stanford PhD friend. Then he was at Rand, and we started working together on stuff, and it was good stuff. And so I felt certain, I started getting offers to go to other places and things like that, but I didn't want to go to any other place.
You were happy at Stanford.
Yeah, the Stanford. Later I was on some program where they gave me some support to do things for the university in general. And one of the things I did was I hired a very good-looking woman to ask a lot of faculty members why they were at Stanford. The good-looking women, that worked good. They answered a lot, and and I tried to analyze the data. Why did people like about Stanford? And I finally decided it was the absence of bad things. The weather's good, the faculty play, and the department pays okay, the housing was okay, and we weren't the best at anything, but we had the least bad things. And that's the way I like being at Stanford. I've always liked being at Stanford. And basically, the university is a well-run university, and it's like Caltech. It's wealthy, and boy, that makes a difference in the United States.
Brad, what was the research or the project that really thrust you into the national spotlight? What was the work that you were doing that resonated even beyond your immediate field?
Um, the only thing I've ever done that's really had outside resonance of any real size was the bootstrap. Uh, Before that, everything I did was within the field, connecting ideas within the field. So I did R.A. Fisher had in his initial papers had wonderful uh, formulas that weren't well understood, and I started understanding them in a geometric sense of curvatures and things like that. And that was the first thing I did that really seemed to get very much attention. Started working with Carl Morris on what's called empirical Bayes. It's a way of using, if you have a large data set, a lot of the same kind of problem again and again, you can use Bayes' theorem without having to have prior opinions, because the data set itself can give you an idea of what the prior opinions should be. And that's empirical Bayes. And I've done stuff like that. So I guess people might have paid attention to it, but statistics is not one of those fields, at least it wasn't one of those fields that electrifies the population or something like that. It's hard to see what the effects are of the field, even though it's very widely used. So I would say about the only thing I've ever done that put me in any kind of public spotlight was the bootstrap. However, I did do one thing, I forgot to tell you this, that made me locally famous. I got kicked out of Stanford when I was a graduate student for writing I became editor of the local, the humor magazine, the Chaparral, and we had a Playboy parody, which I had, my Caltech background did not make it clear to me that some people took religion seriously. And that was a mistake on my part. And I got kicked out of Stanford, and I protested. And they were always kicking out people. And I protested. I was on the newspapers. I was denounced from the pulpit in San Francisco. And for a couple of weeks, I was really well known. That's the only time I think I was ever well known to the newspaper reading public.
What did you write that was so offensive to certain people?
Quite a bit. But the main thing was it was actually a Playboy parody. And the parody, they'd have what they call a ribald classic, where they would take some bit of, classical literature that had something sort of sexy in it. They'd write it up in a way that was more so, it would maybe take a few hundred words or something. And I did a parody of that somehow, unfortunately, involved the Bible. And I really wasn't trying to be sacrilegious. I was really trying to be against Playboy. But that showed my lack of knowledge of the outside world, and I'll blame Caltech for that.
Brad, for the last part of our talk, I want to ask a few questions retrospective of your career, then we'll end looking to the future. Obviously, you switched fields, going from math to statistics. What has stayed with you ever since, just in terms of your approach to numbers or thinking about scholarship that you learned at Caltech?
Well, again, I'll tell you that cleverness has having an idea and not just going bowling into the problem is the only thing that ever works for me. Now, sometimes I don't have an idea, and then it's hopeless. But if you, a lot of people in science, a lot of people in statistics don't really look carefully at what they're doing. They apply big methods, and then these days it's easier to do with the computer, and out comes an answer. What happens if you change the methods a little? What happens if you change the data a little and stuff like that? I've gotten better at thinking about the connections between things. And let's see, I'm doing this method. Didn't I do something sort of similar to that in another area not that long ago or something like that? And so I'm better at connecting things than I used to be. And I have a mental picture of fields. I was the dean for a while. And I imagine a picture of a plane with the origin and some lots of dots where things are known in the field and they're working with Uh, uh, Physics, there's this big, strong cluster of stuff, big dot, lot of dots near the center where people really know things and stuff like that. With statistics, the things are more diffuse. There's a center of the field that's well-known stuff, but then there's points far away that haven't been connected. Right now, for example, those prediction algorithms are points far away that aren't well connected to the main field. And I've always worked by trying to get uh, connections between the things that might apply to any such problem. And sometimes that works and sometimes it doesn't. But when it works, at least you have something that I try and write papers that have some surprise in them. The awful lot of papers when I was the editor were surprise free. You know what they say, what they're going to do. They say what the problem is. Say what they're going to do, and there's no surprises involved. You hear a lot of talks that way too. And I try and always have something that people wouldn't have thought of with easily. You know. So I'm now I've gotten older, and it's harder to do research after a while. Research is energy intensive, and I can't walk as fast or as far as I used to, and I can't think as well as, at least as hard. I think I can still think, but I can't pursue the ideas as well as I used to. Mm-hmm. And so that makes me think there was a lot of energy involved, and maybe there was a time when I really could apply the force and push something through, not by brute force, but by knowing where to push.
Brad, I wonder if you've ever thought about the role of luck in your career, the professional opportunities that you had being in the right place at the right time, and how you might interpret that through the eyes of statistics.
Yeah, so this is a meta question about statistics. Well, of course, I've already told you about the merit scholarship, and it was a lucky choice going to Caltech. I did, without knowing any specific wonderful thing that day that's the thing told me, and that's now I'm the success or something. The idea, what I'd say I should have said about Caltech was that it did raise my game. I realized what it takes to be a frontline thinker. It's sort of like playing in the NFL instead of at college level or something like that. And so that was lucky. The bootstrap came out of my Rupert Miller's work on the jackknife. The jackknife, Tukey was a famous character in statistics and a wonderful researcher, and he invented something called the jackknife, or he co-invented it. And it was a question of how well it worked. It was a way of getting plus or minus quantities for estimates. And Rupert Miller worked on it and wrote a good paper called The Trustworthy Jackknife. And I've tried to understand why that was, and the bootstrap came right out of that. And so that was a lucky break to be told what was an interesting problem. And going into statistics was a good choice for me. I don't know, maybe I would have been a good computer scientist. I don't think so. I'm not really good at technical stuff that much, but I'm really glad I chose that field. So yeah, that was lucky too.
Brad, have you been an engaged alum of Caltech? Have you kept up with Caltech over the years?
No. Stanford absorbed all my interest, and since I went to school there and stayed there, in some sense that made a block between me and Caltech. And the time at our 50th reunion, I did go to the 50th reunion of my class, and that was really nice to do. And Caltech seemed just the same way as ever to me. Went to my old dorm, Ricketts house. Now that they admitted women, I thought to myself, it's going to be a lot more civilized than it was. No, it went the other way. The women were reduced to the level of the guys of being crude. uh, and I was grateful for that. Uh, it was fun walking around the campus again, remembering uh, how much I liked that campus. It was just it wasn't very big. It's at least twice as big now as it was then, maybe more. And I used to walk around it all the time and into the areas around Altadena and stuff like that. I just love that area. So one of the things I like about the Big Bang Theory is that it's at Caltech, and they actually uh, pay attention to or what used to be Trooper Hall anyway. Uh, and so I'm very fond of that, but I haven't participated much. Uh, and it sounds like maybe I do a lot for Stanford. No, I don't. I pretty much stay working. I don't contribute money or anything like that, but I'm very fond of Stanford too.
Brad, in reflecting on all of your contributions, what is it about the bootstrap method that allowed your research to break out of that academic mold and have influence in wider society? What's unique about that one research area?
Well, it has that quality that first of all, the problem's important. It's how do you assign accuracy to a statistical estimate? The older theories require mathematical analysis and making models. So the bootstrap's almost automatic. So in that sense, it's like what I said, maximum likelihood. You can make one program that does it all the time. It's not hard to do. And so, and once you do it and you see how it works, it gives you a different feeling about what accuracy means. So more down to the earth, less theoretical feeling about what when you say that the percentage of Democrats is 54% plus or minus 3%, you get some feeling what that plus or minus 3% means. And it's people like using it because it doesn't require elaborate statistical mathematical calculations. It was the original uh, computationally intensive statistical method. Wrote a paper with Percy Diaconis on for Scientific American computationally intensive methods. It was the first of those.
Finally, Dean, Brad, last question looking to the future. When you're writing your book, what is it that you want the audience to take away? What will an audience truly appreciate through the eyes of a statistician if your book does what you hope it does?
Well, the book starts by talking about the fog of noise that lies over between us and perceiving things as they really are in the world, and how randomness and noise is such a problem in science. Why wasn't there science in the year 20 or something like that? Why didn't the Greeks didn't really have science? They had math. It's because it's hard to see the real world. And the statistical point of view on the world is that there's a smooth, nice truth lying under a very noisy surface. And that if you are able to use probability theory and other theories in an intelligent way, you can penetrate the fog and get at what's underneath there. And that's trying to understand just how random a lot of the things we see are. It came out during the COVID thing that people suddenly really wondered, what percentage of people are dying from COVID? Well, there's a lot of it was a very noisy thing to try and figure that out. It turned out about 1% of the older people who got COVID died. Uh, uh, if it had been 10%, it would be a much different kind of time for the last 2 years. Uh, the so trying to get people to understand something like Bayes' theorem. What does it mean? It's a wonderful way to approach a problem of I have some opinion. How does my opinion change when I get new evidence? Uh, well, the math isn't hard, uh, but you got to know something about probability, and most people don't know anything about probability. Um, Trying to just say that without writing a lot of equations down, so there's no equations in the book. Uh, Trying to say the strength you hold what does it mean? You have a funny shaped coin in your hand. What's its probability of heads? You flip it 10 times, 20 times, 100 times, it comes up maybe 65% time heads. Is there a real probability of heads hidden in that coin? What does that mean? How long would I have to go on before I knew that? That kind of thing. How is information accruing? Does it accrue? Can you get better and better answers if you get more and more data? Not always. Sometimes the noise has an irretrievable lower bound on it. Trying to see the questions of accuracy. What does accuracy mean? What does plus or minus mean? How do you know if new drug's better than the old drug? How do you run a clinical trial? How do you interpret the data in a clinical trial? That kind of thing. So there's big philosophical questions like what is noise and stuff like that, but it's hopeless to try and compete with the philosophers and stuff. But there's the next level of questions is how can we cut through? How can we practically use ideas to get a good idea, get a good picture of what's there under the noise? And that's how statisticians think. What's the bell-shaped curve mean? Why is there such a thing?
Brad, is that to say when you talk about the underlying truth and all of the randomness, are those compatible statements? In other words, is the randomness part of the underlying truth, or is the randomness something to get through in order to see the underlying truth?
Well, you make a good philosopher student because people have answered that both ways. There's theories that say there is no underlying truth. There's only objective is the things that you can do. So one of the theories due to Definity says that I don't know what the probability of that coin is, but having flipped it 100 times, I have a set of possibilities that are more or less reasonable, and that's the only real thing. You can make that set of possibilities smaller and smaller, but there's no real probability of heads of the coin. But the more Plato kind of theory is no, there really is one. You just can't see it. It's sort of like there really is a circle. You just don't have a perfect circle in real life and stuff like that. But as far as interpreting, working with statistics in the real world, those questions are less important because you don't get down to that for most things. You'll be pretty happy if I can tell you approximately what your answer is and approximately how wrong you are.
That's great.
But you want that to be a good answer, not just one I made up. It's not just my authority that says that. There's a model. People have thought of very clever ways of stating the thing you just asked. That make it possible to give reasonable answers. There's nothing like Einstein's theory of gravitation or something that you're not going to ever get that kind of perfection with statistical arguments. But strangely enough, you can make these statements realistic enough so that a rational person will agree, yeah, that's pretty much what we have to decide from this set of data.
And that's a pretty good standard to go by.
Yeah.
Brad, this has been an excellent conversation. I'm so glad we connected. I'd like to thank you so much.
Okay. What